The average man is 70 kilograms, 60% of which is water. So total body water is 42 liters. Try to wrap your mind around a human being having 21 2-liter bottles of fluid inside their body. Kind of bakes your noodle. But this water content is not fixed at 60%. The percentage decreases as you get older and as you become fatter. Peak water is in infancy when you're about 70% total body water and falls as you get older to about 50% in elderly men. Women, because they have a slightly higher percentage of body fat, tend to have less body water than men. Muscle is 75% water. Fat is 10% body water. This can have profound implications for your patients. Let's take an example of a lean 70 kilogram man. How much water does he have? 70 kilograms times 0.6 results in total body water of 42 liters. Suppose this patient then starts to eat a lot of donuts, doesn't exercise, and gains 100 kilograms. What's his total body water now? You'll take the original patient, 70 kilograms and 42 liters of water, and we add on an additional 30 kilograms of fat, which is only 10% water, resulting in a total body water of 45 liters, or 45% total body water, significantly lower than the 60% that we would normally estimate for a young man. This is usually not accounted for in medical calculators. Here's a typical calculator from Medscape that estimates serum sodium concentrations after receiving different IV fluids. If you focus in on how they estimate the total body water, they account for the gender, they account for the weight, but at no point do they account for the obesity of the patient. If you were to use our patient who had just gained all that weight, 100 kilograms times 0.6 because he's male results in 60 liters rather than the correct calculation of 45 liters. Just using gender and mass can overestimate total body water by 33% in this example. Everything in the body is either intracellular or extracellular. These two compartments are divided by the cell wall. The extracellular compartment is further defined into an interstitial space and a plasma space divided by the capillary wall. The relative size of these compartments is super important. The intracellular compartment holds most of the water. 2/3 of total body water, or 28 liters, is intracellular. The extracellular compartment holds the remaining 14 liters, most of it in the interstitial space. In fact, 75% of the extracellular compartment is in the interstitial space and only 3 liters is in the plasma space. 8% of total body water is in the plasma. Now remember, plasma is not the same thing as blood. Plasma excludes platelets, red cells, and white cells, leaving all the dissolved solutes and water to make up the plasma compartment. The intracellular compartment and the extracellular compartments are very different. Most of this difference is generated by the sodium-potassium ATPase, a molecule which continuously pumps sodium from the intracellular compartment to the extracellular compartment and moves potassium from the extracellular compartment to the intracellular compartment. You can think of these two compartments as being differing atmospheres. You have an intracellular compartment with a potassium-based atmosphere and an extracellular compartment with a sodium-based atmosphere. Looking at this in a tabular format, you see that the extracellular sodium concentration is 142 versus 10 millimoles per liter in the intracellular compartment. Potassium, very low in the extracellular compartment at 4, compared to the intracellular compartment at 140. The interstitial space and the plasma space are almost identical. The only difference between these two spaces is that there's a lower concentration of albumin and other large molecules because they cannot pass through the capillary wall. Knowing the electrolyte composition of the compartments allows one to predict how intravenous fluids will behave.